Hello, class. Good morning. Welcome to the last lecture for this course, your statics of rigid bodies. It's somehow going to be also a bit of an introduction to your next course, which comes after this, which is the strength of materials. So we're going to look at more the internal forcing of an object. So it's kind of a preparatory property. So, all right. Moment of inertia, also called as the second moment of area, is a crucial geometric property of a cross-section that determines a beam's stiffness and resistance to bending. So you already experienced this, or perhaps observed this in real life. If you take, say, a plank and place it as if it was a beam supported on both sides, um, with the long side of the cross section laid flat, it will sag if you put weight on it. Whereas if there's a plank, when you have oriented in a vertical sense, like the longer side is standing up, then it still weighs and still carries the same weight. It won't sag as much. So I have here a foam board that's kind of similar to what you're seeing. So if I lay it flat like this and I bend it way, so it makes a lot of bending. But if I put it this way, the longer side cross section is going up, it wouldn't bend as much, right? Though it still bends because it's foam. But if you have harder materials like steel, or in this case wood, it would really resist that, bending. That's practically what it is. It's You could actually resist more load just by reorienting how you arrange your geometry. So, well, in a mathematical sense, it is the product of the area and the square of its moment arm about a reference axis. So in this case, this is your material, but you take a small portion of that and you multiply. So this dA is your representative area, and then you multiply that by this moment arm about x-axis. So if you're making it rotate about that, and then that's how you compute. And then you do a lot of those, right? So you do one in there, another one in here. That's what it's what integrals are for. You're kind of summing it all up. So you do once you cover it up, and once you cover all of that, then you will get the moment of inertia about the x-axis. Okay, so take note that this is important. Your reference axis is very important because you could also get a different moment of inertia about, say, this axis, right? So that's a different moment arm. And then you get area in this area. You get some area here. That's also another one. Okay, so there's also that. And you will see that in action here. So in this class, you will not, I won't let you integrate anything. So that's good. I also won't let you memorize formulas, but I want you to be familiar with them enough for you to use them effectively. So this is a list of um, the moment of inertia for a specific axis, right? So the first one is the BH cube over 12. So this formula is the moment over inertia about the centroid of the axis where you hit the centroid of the object. Now you also have another formula that is the BH cube over 3. That is your moment of inertia about this axis. right? So remember what I mentioned earlier, that reference axis matters. So you have different moment of inertias considering different axes. Okay, so let's try that with this first uh, problem. So first we will try to solve the centroidal moment of inertia. So we will use I bar x is equal to bh cubed over, well, so that's about this axis. That's the centroidal moment, that's the centroidal axis. Okay, so about this axis, we will solve 6 times 3 cube, uh, 3 cube, yeah, apologies for this, over 12. And here we will get 12, 13.5 inch to the fourth power. So take note that this is the unit. So we're not used to seeing this, right? Because the first one is you have a certain um, inch is an area, inch squared is an area, inch cube is a volume. Now, what is inch to the fourth? It's kind of a difficult concept to imagine, but that practically is your area times the squared of your moment arm. Okay. Now, for the how um, about the x-axis? So that's 1x axis. So we will use the second equation, bh cubed over 3. Ix is equal to bh cubed over 3. Sorry, it's supposed to be bh cubed over 3. So that's 6. So I don't want you guys to get confused, right? So if the equation depends on what axis you're looking for. I mean, what a moment area about with axis you're looking for. 6 times 3 cubed. Is equal to, this one's a bigger number because denominators change. 54 to the fourth power. All right, so that's it. Now, I want to teach you guys a transfer formula, right? So if you want to kind of transfer the access, all you need to do is to um, use this equation. So what do you mean by that? So for example, you have a centroidal equation, right? So the let's take I bar x is equal to b h cubed over 12. Now you want to move it to this axis now, the x-axis. So that is a let's use that here. Okay, so we want our from our centroidal, we want to move it to 3 to the x. So that's like 3 out of 1.5. So let's see if we could get the same answer using this one, 1.5. So that's your D. Okay. So if you want to transfer about X, so all you need to do is use that BH cubed. So that's 3 times cube over 12. And then plus your A, that is your 6. And times your area is so base times height times the 1.5 squared, because this one is squared. You will get, you will get the same answer. 12, 6 times 3 times 1.5 to squared equal to 54 inches. So see, they are the same. Okay, next, let's do circles. So in this one, you see that there's an outer radius and inner radius about the centroidal axis. So we could use this one, pi r to the 4 to the 4. But there's, like, an outer and an inner. So meaning the I x. So we use an I bar to indicate centroidal moment of inertia. So I bar x outer minus I bar x inner. So to solve that, it's equal to pi. Let's use a big letter R for our big circle. Oh no. Ah, pi big R over 4 minus pi small r. So if you want to simplify that, it's going to be pi over 4 r big 4 minus. Okay, so the values are 3 and 2. So if you want to solve that, that's going to be 3 to the 4th. Oops. Minus 2 to the 4. So your centroidal moment of inertia is equal to 3 to the 4th minus 2 to the 4th. It is 51.05. And the unit is inches. Inches. That's it. And the last example is a inverted T. So for this inverted T, earlier we did a bit of subtraction, right? Now we want to do addition. And it's also asking to find the moment of inertia about XO, that axis. So we can do, so you could say this is 1, this is 2, area 1, area 2. So I bar, oh no, we could call it IXO. IXO is equal to I1 plus I2 XO. So they will have to have the same reference axis. So how do we do that? Earlier, we learned the transfer formula. What's the transfer formula? I is equal to I bar, which is the centroidal moment of inertia, plus A d squared. Your d is the distance from your um, shape centroid to the new reference to the new reference line. Okay, so that's what it is. All right, so let's try this out. Let's try the first area one. So IXO I1 XO is equal to the pH cube over 12. So again, that's the centroidal moment of inertia. BH cube over 12 plus your area is BH, and then your D1 squared. So D1 is actually this one from the centroid of this shape, area 1. This is D1. Let me do that. D1. Okay. And then D2 is this one, halfway there. This is D2. Right. So we now have I1XO is equal to base is 2 base is 2 times height is it's recovered, sorry, 8 cube over 12 plus, so that's your area, right? So 2 times 4, now D1. So D1 is actually D1 is actually, so it has a bit of a um, formula here because you could see there's Y bar. Okay, so how high is Y bar? So again, that's D1. So how do you get that? You get that by breaking this polygon down. So D1 in this case is Y2. So we're calling this one Y bar. Okay, so it kind of shows your new centroid, so to speak. All right. So so that's the kind of the new centroid location, the Y bar. So let's so we could now try to solve. This is your Y2, then your Y1 is, this, oh, it's too small. Let me do that. So let's draw it with a finer weight lines. So let's put some good labels to this. Okay, again, we will call this one. So this is This is your center D1, and then we call this D2, right? And we'll call this Y bar. So it already has a label. And then we'll call this one Y1, Y2, sorry. And then this one Y1. So we want to go back here and complete our equation. That's Y2. Um, how do we solve for D1? D1 is actually equal to Y1 minus Y bar. So let's just keep it there for a moment. Let's proceed to our next equation. Ix2. What happened to these? So Ix2 Ix I2 XO is equal to this one is, the shorter side is now the letter B. So no, the longer side now is um, B. So 8 times 2Q over 12 plus, why is this 4? I don't know what happened there. 2 times 8 is a Y bar. Now this is 8 times 2 times, how do you solve for D2? D2 is Y bar minus Y2 squared. All right. So now we have these two equations, but we have unknowns, Y bar. How do you solve for Y bar? And how do you solve for Y1 and Y2? It's fairly easy. Y1 is equal to the the distance, it's the centroid, so it's actually 8 divided by 2, so that's 4, plus the height of the first bar, so at the bottom, so that's plus 2, that is 6. Now Y2, wait, sorry, yes, Y2 is just 2, the height encircled, divided by, um, you have the half of 2 is 1. You just have to put, perhaps I could write it here more explicitly so that you will get right away. 8 divided by 2. Really hard time spent. Now, how about Y bar? Y bar is the new centroid, and From your previous lesson, you were able to learn how to find the new centroid from two different composite shapes. Then you will get that by y, is area total, and then area 1, y1, plus area 2, y2. So in this case, y bar is equal to 8 times 2, 16. Let's just write that. And then y1 is 6 plus area 2. That's 2 times 8 times 1. All over 8 times 2, 16. 8 times 2, 16. So divide that, 40. Perhaps you guys will get confused. 8 times 2. So I'm gonna write it all. Oops. So plus. Okay. Y bar is actually equal to 16 times 6 plus 16 times 1 divided by 32. It's 3.5 inches. Now we will plug this values in here. So y1 is 6 minus y bar is 3.5. So here we'll also correct this. 3.5 plus. So I think earlier it was minus, but let me check. Y2, oh yeah, it's subtraction. Still subtraction, sorry. Minus 1. So here, you could now solve. So that's 2 times 8 cubed divided by 12 plus 2 times 8 times 6 minus 3.5 to the power of 2. This is 185.33. Now the other one is 8 times 2 cubed over 12 plus 8 times 2 times quantity 3.5 minus 1 squared. That's 105 point, oops, 0.33. So you add those together, you have your new IXO. So it's centroidal, we could just call it I bar. That is 185.33 plus 105.33. We get 290.60. Yeah, the dot is a bit small. There. And then don't forget your units, inch to the fourth. All right, so that is your moment of inertia about the centroid for this inverted T section. So I hope you guys learned something new. You were able to catch up on the discussion, but if not, feel free to play this back or check out other videos, that might be helpful to for your understanding. So yeah, thank you very much and good luck on your quiz and your finals exam next week, which will cover equilibrium, first and foremost, equilibrium, and then you also cover the method of joints and method of sections. And lastly, this one, moment of inertia. Okay, so thank you everyone and have a good day.